Independent events. Objective: to use the laws of independent events and mutually exclusive events to solve probability problems. That's kind of what we're going to do this lesson. We're all talking about using these two laws we haven't really talked about yet: independent events and mutually exclusive events to solve problems. So it's basically like we're kind of wrapping up this whole chapter. We're going to do all the same things we did before. We're going to do tree diagrams, we're going to do Venn diagrams, we're going to do probability laws, and now we're going to have more things we can ask. And that's kind of what's going on here. First, let's look down here. If two things are independent, then there's a special formula we have for them. That's this right there. Probability of A times probability of B equals probability of A intersection B. This formula, which is also in your formula sheet, and I'll show you that in a second, works both ways. If you have this, then it means that. But this is only true when A and B are independent. Right? Independent means they don't mess with each other. Like they don't affect each other's abilities, as it says right here. It does not affect each other's occurs. So what's another big thing about if they're independent? Well, then the given that does nothing, right? Probability A given B, or A given not B. Well, it's independent. That does not matter. If they're independent, it does. That's how you spell does not matter. Right? So again, only if it's independent, that means A and B have no effect on each other. So probability of A given B, who cares? It's just probability of A. Likewise, probability of B given A. If they're independent, A doesn't matter. So this is going to be probability of B. Again, only if it's independent. Very important. You can't assume it's independent. That's the number one rule. They have to tell you. They're going to be like, hey, these two are independent. Then you could use the formula. Then you could do this, or more importantly, you could use the formula right here. So again, it's only when they tell you. You can't assume that they're going to tell you or they're going to ask you, are these independent? And then you can use the formula. Let's look at the formula right here. So again, this is in your formula sheet. Independent events, probability of A intersection B equals probability of A B. Again, the thing I gotta stress the most is you can only use it when they tell you. Only when told independent. Only time. Right? If they don't mention independent, you can't just go, oh, it's independent. No. Only when they tell you. It's the only time you can use this formula. Cannot stress that enough. That's the number one mistake people make. They just use it willy-nilly. Only when they tell you. Now let's look at other formulas that we're going to use also. So starting here, probability of NA, right? This is our thing I always say, right? 1 over total. It's the key to life in stats. Right, so that's all that we've been using. Complementary events, remember that's just the opposites, A and A prime. So this one actually always works also, right? I mean, something you should just have pretty much memorized, right? A plus A not equals 1. The way we tend to use it is we have one of them, like we want to find A prime, we just go 1 minus probability of A. That's what we tend to use it the most, but that's the formula in your formula sheet. Then we get down to these two. Then we get down to these, which we haven't really talked about yet, but we're going to talk about more today. Combined events, right? It's our best friend. This is the one that always works. Yay! We love this one. This one always works. Right? So don't forget this one. Super important. It always works. Right? You guys can laugh, but that's a pretty good heart based on how I have to draw. Better than my lines. Okay. Mutually exclusive events. Now we haven't talked about this really enough. Mutually exclusive, it's kind of like independent. Only when they tell you. When they tell you, you could use this. But really, I don't use it this often. Mutually exclusive, what I do, you show what that means. That means that the intersection is 0. They have nothing in common. So that's really how I use it. If I hear it's mutually exclusive, oh, I know intersection is 0. Right? You can see right here it's the same thing. Notice how these formulas are the exact same thing except that this is 0, so they don't have it. That's why. But that's what I think. So when they tell you mutually exclusive, again, only when they tell you, only when told, could you use this? You could use the fact that you could use this formula, or you could use the intersection equals 0. That's what it means. Conditional probability, we talked about already, right? That was our last video. Right, this is a given that. So when you use this, when they say given that, that's when you use this thing. If you hear the words given that, and then you use this formula right there, right? That's what this line means right there. So only when they say given that, to use that formula. Only time. And then we already talked about, but independent events, much like mutually exclusive events, when they tell you, if they tell you independent events, or if they ask you, you're just like, oh, are these two things independent? Then you can use the independent events formula. But again, only when they tell you. So mutually exclusive and independent, keep very conscious. It's only when they tell you. Could not stress that enough. Now let's do an example. So right here. Suppose probability of A equals 1/2, probability of B equals 1/3, and the union equals P. Find a union, find P, if they are mutually exclusive. So again, notice how they tell you right here? Oh, they're mutually exclusive. So you use the formula. Probability A union B equals probability of A plus probability of B. It's our normal formula with this thing being 0. And you just kind of plug stuff in. Okay, I got A, 1/2. I got B, 1/3. Do a little common denominator. Multiply this by 2/2. Multiply this by 3/3. Now you get 3/6 plus 2/6, also known as 5/6. And that's the union. If they're mutually exclusive. Again, notice I only use this because they told me. Right? They told me they're mutually exclusive, so I use the formula. Now let's look at this one. Find A union B if they're independent. Now independent, if you look at the formula for it, it's this thing. Sorry, times. Right, that's the form for independent. You're like, that doesn't give me the union. Well, don't forget our best friend. The guy that always works. Right, this thing right here. Probability A union B equals probability of A plus probability of B minus the intersection. So our game plan here is, wait, I could find this out using the independent formula. So use the formula. So probability of A is 1/2. Probability of B is 1/3. So I get 1/6. That's what this is. So now I have the intersection because they're independent. I can use the formula. I have A and B is given 1/2 plus 1/3. I can find out what the union is, right? Put all the common denominator. 3/6 plus 2/6 minus 1/6. If you do all that correctly, you're going to get 5 minus 1 or 4/6. Don't need to reduce it because it's IB. Right? But that's the idea. If they tell you to mutually exclusive, go ahead and use it. If you have to find the union, anytime I have to find a union, I'd like to use this formula. Even with this, I just kind of use this formula and plug the 0 in there. That's just the way I roll. But this formula, again, especially with union, always works. It's a good way to find stuff. And the fact that they're independent helps you find the intersection. You just go, find the intersection first, multiply them. Since they're independent, you could do that. And then plug it in, solve. Let's move on. So look at this one. Probability of A equals 2/5. Probability of B given A equals 1/3. And probability of B given not A equals 1/4. Find probability of B and probability of A intersection B. For this first one here, how do I find B if I have A, B? Now, I'll keep note they didn't say independent, so I can't use the independent formula. They did not say mutually exclusive. I cannot use that formula. So the only formula I could use actually is, I have a given that. So let's use the given that formula. I'll just write the full formula here. Probability A intersection B equals probability of A times probability of B given A. So with this, I don't know what the intersection is. I do have probability of A though, so 2/5. And I have probability of B given A, that's 1/3. So the intersection is an equal 2/15. Right, and you're like, how does that help me? Well, let's just create a picture first. Right, they also give me this, so I gotta use this too. So let's do that, given that formula. Right, same idea. Right, it's the exact same as this formula that's in your formula sheet. Only difference is now these are all the knots. So let's see what we could do there. So A naught intersection B is equal to probability of A naught times probability of B given A naught, not A. Now again, there's a couple things we know. I know this one, that they gave it to me, 1/4. I should know this one, right? If I know what A is, I can figure out what not A is. That's 1 minus probability of A. So 1 minus 2/5, also known as 3/5. So I know this one also. Multiply together, I get 3 out of 20. So now I know what A intersection B is. Sorry, yeah, right here, 2/15. I know what A, not A intersection B is. But I don't really have no idea what B probability B is and what the probability of A intersection B naught is. So to help us figure out what all this stuff is, let's make a Venn diagram so we can kind of picture it all. So it's going to be like this. Here's my A, here's my B. Now, a little trick to make this a little easier, I'm going to put this in decimal form. Otherwise, it's going to be too much of a mess to try to figure out what everything is. So 3 out of 20, 15. 2 out of 15 is about 0.33. This is me 0.25. This will be 0.33. And this will be about 40%. Right, so in this case, remember A is all the circle, the whole circle, so that's 0.4. I could do some fractions, but it's a little easier with decimals. The intersection we found was 1.133. Now look at what we found here. A, probability of A prime and B. Right, so not A, but you're in B. So that's this part right here. So this is 0.15. And look at this A not B, right? A but not B right here. Well, if all of A is 0.4 and that's 0.113, A intersection not B is going to be 0.4, which is all of A, minus off the part of B you don't want, 0.133, which would be about 3.67, 0.367 ish. So there's that. Right, and if I want the probability of B, well, I have all of B right here. That whole, remember, it's the whole circle, not just that little part. So now that I figure out what this part is, I have probability of B. That's just going to be 0.133 plus 0.15, or 0.283, roughly, approximately. Let's go right there. And if I want to find out what probability of A intersection B is, B naught is, right? Well, that's, I want A but not B. That's this guy right here. Right? That's this little side right there. That's A but not B. So 0.367. And that's how you do that problem. Let's move on to the next example. So two independent events A and B are such that probability of A is 0.6, probability of A intersection B is 0.2. Find probability of B. So a couple things. First, again, notice that they say two independent events. So since it's independent, that's me getting used to the board here. Since it's independent, we can use the formula, right? Okay, it's independent. That means I could do this from your formula sheet. Right, probability of A times probability of B. It's a B. Say this a little bit more like a B now, right? Since they tell me it's independent, I can use this formula, and I know what this is, 0.2, based on what they gave me. A is 0.6, and I'm looking for probability B, so let's put an X there. Right, now it's a very simple problem to solve. Oh, you want to solve for X? Just divide by 0.6, right? Since I know it's independent, I can use the formula, and I get this, and I get X is equal to, just move it over, 2 over 6, or 1/3. That's the probability of B. Right, again, all that started from the fact that they told you there's two independent events. You can only use this formula if they tell you they're independent. If they don't say anything, you can't use it. And then the next part of this, part B of this, says find intersection. And how are you going to find that? The same way we always find that. We use our favorite formula. Probability of A union B equals probability of A plus probability of B minus the intersection, right? That formula is one formula that always works, right? And we have everything we need now. Probability of A is 0.2, 0.6. I was looking at the wrong thing. Sorry about that. Probability of B is 1/3, or 0.33, minus probability of A intersection B, which is 0.2. Right? Do a little math. 0.6 minus 0.2 is 0.4. 0.4 plus 0.33 is 0.733, about, roughly. Right? And that's the idea. Right? Again, if they tell you it's independent, then feel free to use the formula. If they don't, you can't. And what you do is easy to find enough to find probability B. The way you find a union, it's pretty much always the same. Just use that formula. Just plug it in. Let's do another example of this, but with a little bit of a twist. Two events A and B are such that probability of B equals 0.4, probability of A union B equals 0.7. So now they give me B and they give me the union. Look what this one says. This is a typo. Just say probability of A. Given that A and B are mutually exclusive, find the probability of A. Same thing there. So the key to this is you gotta remember what mutually exclusive means. It's in your formula sheet a little bit, but really what mutually exclusive means is that they have nothing in common. So the intersection is 0. So what I would do is use the formula we know. So you could just say that, or if you're looking at formula sheet, you get this formula, which is just our favorite formula minus that. They don't have that because that's 0. So this is in your formula sheet. If that's a typo, this is in your formula sheet. Sorry. And look what happens. You have everything you need. A union B, 0.7. Probability of A, we don't know, that's what we're looking for. Probability of B, well, that's 0.4. Do a little math, and you get probability of A equals 0.3, 0.7 minus 0.4. That's how that one's done. Right? So if it's mutually exclusive, it means the intersection means nothing. It has nothing in common. And then you can use the formula. Now, if they're independent, right? So this one says, given they're independent, starts a different problem. Start brand new. Independent, that means something different. That means the intersection equals the two things times each other. So in that case, let's put down what we know. We know this is 0.4. I'm looking for this, so that's x. And I make this, I don't have it, so all I know right now that is 0.4x. Because I don't have anything. So how am I going to find A if I have that, which I really don't know? I have A I don't know, and B is 0.4. I still got to use this. Remember how we use that? You remember how we bring that into the fray? We write it down our favorite formula. The one that always works. I'm not sure if you guys believe the fact that it always works. It really does. Well, in stats. Right? It's the one we always go back to. It's always true. Right, we get that. I don't know the union. Oh, yes, I do. Haha, that's 0.7. I don't know A, that's X. That's what I'm looking for. B is 0.4. And this, well, since it's independent, that is just X times 0.4 or 0.4x. Right, now you look at it, it's just a math problem. Subtract off the 0.4, I get 0.3. Add these two together, or subtract them, I get 0.6x. Divide by 0.6, right? 1x minus 0.4x is 0.6x, divide by 0.6. If you reduce that, you get 1/2 equals the probability of A. Right? That's the way it's done. But the key thing about this is just, look, it's like knowing your vocab. If they tell you mutually exclusive, that means this. They have nothing in common. Or you can just use the formula. If they say they're independent, that's this thing. Right? And then you use it. In this case, it's a little tougher, so you gotta plug it back in. But this is always true, right? Independent means you're probably gonna have to use this thing. That or the fact that the conditional probability doesn't really matter. If they say they're mutually exclusive, you're probably gonna use this thing. So some things to keep in mind. Next example. This is more just like a rehash of everything to make sure we understand the concepts before we move on to our final concept for the day. So this first part. Probability of A equals 0.11. Probability of B equals 0.7. And the number in B is 14. So first I want you to find the probability of A naught, right? Remember that's just everything that's not in A. So that's just 1 minus that. So 1 minus 0.11, 0.89. So that's A not, or not an A. The number in the universe? Now, if B is 14, this is like a basic math problem actually, kind of. If B is 14 and B is 70%, well then, if you divide 14 by 70%, you're gonna get the number in the whole universe. 14 divided by 70% is 20. So the number in the whole universe is 20. Right? Because if you do 0.7 times 20, you're gonna get 14. So how do you go backwards? Well, you get the total you have divided by the percentage it's supposed to be, and you get the total value, 20. Now look at the next one. B 1. If any of your independent events, right? That means probability of A times probability of B. So in your formula sheet, equals probability of A intersection B. Remember, you could only use this when they tell you, and they told me. So do you want me to find the intersection? Well, I have probability of B, luckily. And I have the probability of A, 0.11. You just multiply them together, and you get 0.77. Done. Now B's trying to be a little tricky, or I should say B2 trying to be a little tricky. What's the probability of A given that B? When I talk about this at the beginning of class, if they're independent, in fact, the fact that it's probability of A given B does not matter at all. They're independent. I don't care what you give me. It's just this. It's probability of A. Right? They're independent events. It doesn't matter who went first. Right? Because that's what given that is. Given that is A given that B happened. So B already went. Doesn't matter. It's independent. So probability of A, which is 0.11. So that's B. C says instead, how if they're mutually exclusive? Find union. Right? Well, if they're mutually exclusive, and I want to find the union, well, so probability of A union B, I can use the formula, right? So again, when you do these, it's all about what's the definition. Mutually exclusive means they have nothing in common. Mutually exclusive means A union intersection B is 0. That's what it means. They have nothing in common. So if you use this formula, the one in the formula sheet, probability of A plus probability of B, it would normally be minus that, but that's 0, so you're good. A, I have 0.11. B, I have 0.7. Add them up, and you get 0.81, right? 0.11 plus 0.7, 0.81. So again, independent, use the independent formula. Mutually exclusive, use the mutually exclusive formula. What does it mean in general? Independent means that A and B don't affect each other, and mutually exclusive means that they have nothing in common. Let's go to our last type of problem, and this is solving an at least question. This is just for ease, to make life easier for you, right? So when I send an at least question, the big trick to finding an at least question, that takes forever. The big trick is that's what it says right here. It's a lot easier to figure out the complement. At least one, I always like to say, like, if you haven't trying to figure out what's the difference between at least and at most, think about it like food. I want at least one cookie, so one or more. Right? Now, what's the complement of that? What's the opposite of that? None. Right? If you want at least one, the complement is none. Right? So that's what it says right here. Probability of A prime, which we know is 1 minus the probability of A. Probability of at least one, well, the opposite of that, it's 1 minus probability of none of them. And if you do that, it makes your life so much easier. Instead of trying to figure out how to get at least one, right, which a lot of times would be like AA, A not A, not AA, all that stuff where you're going, oh, I want at least one blue, so it's like red, blue, yellow, red, yellow, blue, red, red, red. Like it's all this. Instead of doing all that, you just do 1 minus the complement, 1 minus none. That's right. Just keep that in mind. The opposite of at least is none. Right? The opposite of at least one is none. So let's look at a couple of examples where we do this, and then we'll be done for today. A two dice are rolled. That's a weird sentence. 2 dice are rolled. Take the A out. That's me saying that. What is the probability of rolling in 6 on at least one of them? Right, so 2 ways to do this, right? You could try to figure out what's the odds of rolling 6 on at least one. So you're 6 on the first one, and then not 6 on the second one. You could do a little T diagram if you want. Right, how about not 6 and 6? And then how about 6 on both? Right, so you can figure out all those, and then do math on them up. But what's easier is doing the complement of this. Remember, the opposite of at least one is always 1 minus probability you did none of them. So let's do that. Same thing. 1 minus probability of none. You roll no 6. We're rolling a die here, right? So we have 1, 2, 3, 4, 5, 6. We want the odds of not getting a 6 at all. So these 5. So if not rolling a 6, you have a 5 out of 6 chance on the first die. And on the second die, keep in mind these are independent events, right? The second die, when you roll die, whatever the first one gets does not affect the second one at all. They're independent events, so it's the exact same odds. 5 out of 6. So you go 1 minus 5 of 6 times 5 of 6, or 1 minus 25 over 36. Common denominator. And you get 11 out of 36. That's odds of rolling at least 1 6 when you roll 2 die. Let's do one final example here. A, B, and C have 10%, 20%, 30% chance of independently solving a certain math problem. Math, by the way, with an S, that's an UK thing. You should watch some British TV shows; they're amazing. If they all try independently of one another, what is the probability that at least one of them will solve the problem? This is the exact same problem we just did, right? We have A, B, C. And it says what's probably at least one of them would serve. So let's do 1 minus probability that none of them would do it. Right? So probability of A is 10%, 0.10. So not A would be 0.9, right? 1 minus 10%. Same thing for B. B is 0.2. B prime, right? Opposite of that, 0.8. C is 0.3, C prime 0.7. Right? So these are this is a chance that none of them are gonna solve it. Like that A doesn't solve it, B doesn't solve it, C doesn't solve it. Now all together, remember the independent events. So how do you do all of them together? Independent events. So use the formula. Right? Just multiply them all. That's how you do independent events. So for us it's gonna be probability of at least one is 1 minus probability of none. And probability of none is all this multiplied together. So 1 minus 0.9 times 0.8 times 0.7. You do all that correctly and you're going to get 1 minus 0.5 or 4 or 0.496. They have a 49.6% chance of at least one of them solving the problem. So it's not bad. And that's this lesson.